Let's talk about Gauss's law. And first, let's start by talking about electric flux and defining what electric flux is. So suppose you have an electric field pointing to the right and its constant electric field in space. And suppose you have a rectangular sheet that's coming out of the page with dimensions A by B. Then these field lines are going to be going through this surface. Okay, and then what would happen, suppose you rotate it at some angle like this. Okay, then the electric field lines that are going through this rotated rectangular sheet are going to decrease, right? Because these electric fields down here, they're not going to be going through this rectangular sheet. And if you take the extreme situation when the sheet is completely rotated 90 degrees, then none of these field lines are going to be penetrating this rectangular sheet. Okay, so electric flux is a measure of how many electric field lines are penetrating your surface. Okay, and it can be quantified by the formula that electric flux is equal to E dot area. Okay, electric field dot product with the area. Okay, so we know that electric field is a vector. How does area become a vector? Well, it becomes a vector because we say so. Okay, so if we're making a vector, we have to define its direction. Okay, so the way the direction of the area is defined is it is perpendicular to the surface. Okay, so suppose you take this one, this case over here, then the area is going to be pointing upwards. Okay, if your surface is this one, the one that we started out with, then your area is going to be pointing to the right. Okay, and if you take this one, when it's slightly rotated, then your area is going to be pointing to the slightly off angle. Okay, so here are these electric field lines, and this is the area vector, and this one is the area vector for this one, and this one is the area vector for the original picture that we started out with. Okay, so here you see that area is parallel to the electric field, so this dot product simply becomes a product. So for the first case, the electric flux is the electric field times the area, which is A times B for the first case. Okay, for the second case, we're going to have E naught times the electric field times cosine theta. Okay, because it's a dot product and this is the angle between the area and the electric field. Okay, and it happens that this angle is the same as this angle. Okay, and then in this case, third case, the electric flux is E naught times A times B times cosine of 90, which is 0. Okay, so the electric field for the third case is 0, and this one is maximum, and this one is, somewhere in the middle. And this is 0. Okay, so this is how electric flux is defined through a surface. Again, it's a measure of how many electric field lines are penetrating your surface. So now that we know what flux is, we are ready to define Gauss's law. Gauss's law says that integral around a closed surface of E dot dA is equal to the charge enclosed by the surface divided by epsilon naught. Okay, where epsilon naught is the permittivity of free space. So the left side might look very intimidating, but if you're doing Gauss's law problems and your problem is getting very hard and the math is not simplifying, then either you should not be applying Gauss's law or you may be doing something wrong. Okay, so it should simplify very easy if you're on the right track. So we know what electric field is, okay, from the previous lecture. Hopefully you know what dot product is. So dot product means that if you're multiplying two vectors, then E, so say you had two vectors A dot B, then A dot B is equal to magnitude of A times magnitude of B times cosine theta, okay? Where say this is A, this is B, okay, and this is theta. Then B cosine theta would be the projection of B onto A. Okay, so that's what dot product is. It's one vector times the projection of the second vector on the first vector. So so if two vectors are not parallel, you have to find the component of the second vector that's parallel to the first vector and multiply the multiply them together. Okay, so the reason we had this dot product is, remember when we had that rectangular sheet and we were rotating it at different angles, and when we rotated it slightly, then the electric flux decreased, and when it was completely rotated so that no electric field lines were going through it, then the flux was 0. That's what the dot product is controlling, is how much flux is going through your Gaussian surface. Okay, so dA is your Gaussian surface, and you get to choose what your Gaussian surface is going to be, and you choose it so it makes your problem easy to solve. Okay, it's a three-dimensional surface that you choose. Okay, and then you integrate over the closed surface, and that is equal to the electric flux. Okay, and electric flux is equal to the charge that is inside that surface divided by E naught. Okay, so that's what these quantities mean in Gauss's law. Okay, so dA, we talked about it briefly, that it's a vector and its direction is perpendicular to the surface. But remember, our sheet was like this, and we said, okay, well, the A is perpendicular to the sheet, so it's going to point like this. But this is also perpendicular to the sheet the other way. So which way do we pick to be the direction of the area? Okay, so the way we do that is, suppose instead you had a cube like this, then the direction of the area of this face is going to be outwards. Okay, so if it's a closed surface, then the direction of the area is always outward from the surface. Okay, so for the top it's going to be upwards, for the left it's going to be to the left, for the bottom is going to point down, for the front is going to come out towards you, and for the back is going to go back towards the screen. Okay, so the direction of the area is perpendicular to the surface, and it always points outwards from a closed surface. So suppose you had a sphere, then what is the direction of the area? So it's going to be perpendicular and outwards, so area is going to point like this from a sphere. Okay, now that we have seen Gauss's law, let's do some problems that further clarify what everything means. So suppose that you have a cube, Okay, and you have a charge, say Q, that is right in the middle of this cube, inside it. Okay, then what is the flux through this cube? So remember, Gauss's law was E dot dA equals charge enclosed over epsilon naught. Okay, so in this case, our charge is enclosed by this cube. Okay, so then what is the flux through this cube? The flux is the Q divided by E naught. Okay, so we don't even have to mess with the left hand side here because we know what is a charge that is enclosed by our surface. So now that we know what the total flux through this cube is, what is going to be the flux through just one side? Okay, so if the charge is right in the middle, then the flux would be, okay, so flux through one side is going to be Q over 6 E naught because there are 6 sides to the cube. Okay, so what's happening is you have these field lines coming out of the charge radially away. Okay, and then when you sum up all the electric fields, multiply by the areas, then you end up getting Q over E naught. Okay, so if you were actually doing the left hand side, it would have been really complicated because E and area are not always parallel. Because area, let's say you take this bottom face, is going to point downwards, but look at this electric field lines. This one is not parallel to the area, so you can't just multiply these two. Okay, so with the right hand side, we were able to get the total flux, and then because this charge was right in the middle, we were able to figure out that the flux through one side is just 1/6 of the total flux. But say this charge was not in the middle but somewhere in the corner but still inside, then the flux through this cube would still be Q over E naught, but flux through one side would not be 1/6 times Q over E naught because now the charge is not right in the middle of the cube. Okay, so we found the flux that is produced by the point charge that is inside a cube. Okay, so what if this point charge was enclosed by a sphere? Okay, so say this is a sphere of radius r. Then what is the flux through this sphere? Flux would be the charge enclosed, which is Q over E naught. So again, the same thing. Okay, because flux is nothing but the charge that is enclosed by the surface. Okay, so it's simply Q over E naught. What if there was another plus 2Q over here? Then what is the flux through this sphere? Then it's 3Q divided by E naught. Okay, and if there was another minus 3Q here, then you add up all the charges, it becomes 0, so the flux is 0. Okay, so flux is nothing but the charge enclosed by the surface. Okay, so now let's say you take your cube again, but this time say you have electric field lines entering your cube. So say this is the electric field pattern in the space that the cube is sitting in. Then what is the net flux through this cube? Okay, so now we don't know what the charge is inside the cube, so we cannot just say that flux is equal to charge over E naught. Okay, so we have to actually do the left hand side of Gauss's law. Okay, so the way we're going to do that is we're going to add up the contribution of each side of the cube to find the total flux. Okay, so first we have to find the area or the direction of the area. So for the left face, it's going to point outwards to the left. So for the left face, it's going to point outwards to the left. For the right face, it's going to point outward to the right. Top is going to point up. Bottom is going to point down. And front is going to come towards you. Back is going to go back. So then electric field lines are going to be perpendicular to this and this. So the top and bottom don't matter. Neither do front and back. Okay, all that matters is the left. Okay, and the flux that the left is going to produce, flux produced by the left face, is equal to E naught times the area. But it's going to be negative. Okay, and then the flux to the right face is going to be E naught times area, A squared, which is area. But this is going to be positive because electric field and the area are pointing in the same direction. So when you add these two, you end up getting that the net flux is equal to 0. Okay, so that means that the electric field lines that are entering this cube are also leaving it. So the net flux ends up being 0. Okay, so that's what that's why the flux is 0. So that means, what else does it imply about charge? If flux is equal to 0, then there is no net charge inside the cube. Okay, now let's say, there's electric field lines entering, but say what's coming out is equal to E naught. Okay, so now what's the flux going to be? From to the right is going to be 2 E naught times A squared. From the left is going to be what it was before, E naught A squared, and negative. So then the net flux is going to be E naught times A squared. Okay, so this time there is a net flux. So what does that imply about charge? This means that there is some charge inside the cube. How would you find that charge? Well, you know what the flux is, and so you said the flux is equal to charge enclosed divided by epsilon naught. So charge enclosed by this surface is epsilon naught times electric field times A squared. Okay, now let's say you have a charge in space, say it's Q, and you have a sphere here. Okay, and so you're gonna have electric field lines going through the sphere. Okay, and then the rest of the pattern is gonna look like this, radially away. Okay, so then what is the electric flux through the sphere? Okay, electric flux is 0 because this charge is outside the sphere. Okay, but it doesn't mean that there is no electric flux going through the sphere. Okay, it means that whatever electric flux enters the cube, it also leaves it. Okay, so the net flux is 0, and that implies that the charge is 0. Okay, so that was a last of flux. So Gauss's law, okay, says E dot dA equals Q enclosed over E naught. Okay, so it has electric field appearing in it. So it's also useful for finding electric fields for distribution of charges. Okay, so suppose that you have a point charge Q and you want to find the electric field that's produced by this Q. And remember, the electric field produced by a point charge is equal to kq over r squared. So we already know the answer from previous video. But here let's do it using Gauss's law. Okay, so first thing you have to know about your charge distribution when you're using Gauss's law is the field pattern. So you need to know the E field pattern. Okay, so, and we know that the electric field pattern looks like this, radially away. Okay, and then second thing you have to do is you have to pick a Gaussian surface that makes your problem easy. Okay, the Gaussian surface that's going to make your problem easy is going to be the one that gets rid of this dot product. Okay, because until you get rid of this dot product, you cannot do anything. You cannot integrate. Okay, so in this case, if your field is radially away like this, what kind of three-dimensional surface is going to get rid of the dot product? A sphere. Right? Because if you take a sphere, it looks like this. Then the dA for the sphere is always radially away. Remember we discussed that? So dA is radially away. And here, here, and here. Okay. So what that does is, because the dA is always parallel to the electric field, this dot product goes away. Okay, so we picked a Gaussian surface of radius r to be a sphere, and that gets rid of the dot product. Okay, so the dot product just becomes a product. It becomes E times dA equals the charge enclosed, which is little q over E naught. Okay, so first thing we have to know for Gauss's law is field pattern, and then you choose your Gaussian surface so that it gets rid of the dot product. Okay, and then the integral sign is still here, so we're integrating over the sphere. So okay, so our integral is over sphere. Okay, so now what do you know about the electric field value at the edges of the sphere when r is constant? So if r is constant, then the electric field is also going to be constant. Okay, so what does that mean? What does that imply about electric field? It can come out of the integral. So electric field comes out of the integral, it becomes E times integral of dA equals q over E naught. Okay, and the dA for a sphere is 4 pi r squared equals q over E naught. So that implies that E is equal to 1 over 4 pi E naught q over r squared, and 1 over 4 pi E naught is k. Okay, so this is kq over r squared. Okay, so Gauss's law gives you electric field at all the points that are the boundary of your Gaussian surface. Okay, let us now consider a spherical conductor. So say this is a conductor that is not hollow. Okay, and then say you put some charge plus q in this conductor. Okay, so conductors have this property that whatever charge you place on a conductor, wherever you place it, it all goes to the surface. Okay, so after a while what's going to happen is, on the same conductor, so suppose its radius is capital R. Okay, so all of this charge is going to go to the surface. Okay, so this q goes to the surface. And say our objective is to find the electric field for r less than r and r greater than r. Okay, so for r less than r, we're gonna r less than r, there is no q, right? Because there's no q inside the conductor. So if you draw your Gaussian surface, say you draw a sphere like this, then you would say that E, or integral E dot dA equals Q enclosed over E naught. But Q enclosed is 0, but your Gaussian surface is not 0, because that can be anything, right? So that implies that electric field is 0. Okay, and that's always true for conductors. Electric field inside a conductor is 0. Okay, so R less than the radius of the conductor, electric field is 0. Okay, what about R greater than R? Okay, so you have to know the field pattern. The field pattern looks like this. Okay, for this conductor, it's radially away. So if it's radially away, then what do you think is a good Gaussian surface? A sphere. Okay, so we're going to take a sphere of radius r, or small r, to be our Gaussian surface. Okay, and then we're going to say that E dot dA is equal to Q enclosed over E naught. Okay, so because our Gaussian surface and electric field are parallel, the dot product goes away. It becomes a normal product. Okay, Q enclosed is little q over E naught. Okay, electric field is constant, okay, over this Gaussian surface, because this situation is symmetric. So electric field comes out of the integral. It becomes integral of dA equals q over E naught. Okay, so that implies that electric field is equal to 1 over 4 pi E naught q over r squared, because the dA was 4 pi r squared when you integrate it. Okay, so the electric field outside a spherical conductor is the same as the electric field produced by the point charge, and the electric field inside the conductor is 0. Okay, so instead of a conductor that was not hollow, suppose it was a hollow conductor, and you put some charge q on it. Okay, and then you were asked to calculate the electric field inside and outside. Then you would get exactly the same answer, okay? Because you're gonna say, well, that there's no charge inside the conductor, so that inside this hollow conductor, so that implies that the electric field is 0. And outside, when you draw your Gaussian surface, you're gonna take a sphere again, and you're gonna end up getting the same expression. So whether your metal is hollow or not, as far as the distribution of charges and the electric field that's produced, it's the same thing. Okay, so, and what if this was not a metallic hollow sphere? What if it was an insulator with the same distribution of charge? Then exactly the same thing. If you work it out, you would get exactly the same thing. But say you had an insulator. Okay, so let's do this on a clean sheet. So say you had an insulating material, and it's a sphere, and it's uniformly charged like this. Okay, suppose the total charge on it is Q, and let's say its radius is R, and we have to find out the electric field again for R less than R and for R greater than R. Okay, so for this problem, it's a lot easier to find the electric field on the outside. Okay, and you'll see in a second why that is. Okay, so if you're on the outside, so first of all, the electric field pattern of this sphere is going to look like this. Okay, radially away. Okay, and then if you're on the outside, you know, if this is the pattern, then the best Gaussian surface is a sphere. So you take a sphere of radius r. Let's do a different color. So you take a radius, or you take a sphere of radius r. Okay, and then you say that E dot dA equals charge enclosed over E naught. Okay, and the charge enclosed by the blue sphere is the capital Q over E naught. Okay, so this side becomes E times 4 pi r squared equals Q over E naught. Okay, so E becomes 1 over 4 pi E naught, which is K, Q over r squared. So that's the same as for the case of the conductor, or the spherical conductor, or a point charge. But what if you're inside the sphere? So if you're inside the sphere, you're gonna draw your Gaussian surface like this. Okay, so now you're only enclosing this charge. You're not enclosing the charge that is outside your Gaussian surface. So now your radius is this small radius, and the charge that you have to, the charge that's being enclosed is the charge that is inside this blue sphere. So how do we find that? Okay, so to find that, you define the density of charge on the sphere as total charge over total volume. And to find the charge that is enclosed, that is going to be your density times the enclosing volume. Okay, so it's going to end up being Q over 4/3 pi r cubed times the enclosing volume, which is 4/3 pi times small r cubed, and that's gonna equal Q times r cubed divided by capital R cubed. Okay, so that is the charge enclosed by the sphere when you're inside the insulator. Okay, so to find, oh, we switched it, didn't we? This should be r greater than r, and now we're doing r less than r. Okay, so you're gonna do E dot dA equals the charge enclosed over epsilon naught. Okay, so E, the dot product goes away, E is constant, so it becomes E times 4 pi r squared. Q enclosed we just found, and that was the hardest part of the problem, r cubed over capital R cubed times epsilon naught. Okay, so E is equal to Q times R over 4 pi E naught R cubed. Okay, so that's the field inside an insulator that is spherical and uniformly charged. Okay, so now let's take a case where our Gaussian surface does not have to be a sphere. Okay, it happens to just keep being a sphere for all the cases that we've done. Suppose you have a rod that is uniformly charged and it's infinitely long, extends on both sides. Okay, and we have to find the electric field that is produced by this rod. Okay, so first we have to know the field pattern. What is the field pattern going to look like? Okay, say you're here in space, then this charge is going to repel it or it would repel the positive test charge that we are testing our electric field with. Okay, and this charge here is going to repel it here, but there is some corresponding charge over here that is going to repel it the other way, so the X component is gonna cancel. Okay, what about up here? Same thing, the X component is gonna end up canceling. Okay, so this charge is gonna repel it this way, this charge is gonna repel it this way, so the X component is gonna cancel. So your field that is produced by this rod looks like this. Okay, it goes radially away, and this is in 3 dimensions, so we're only seeing 2 dimensions on this screen. So what is the best Gaussian surface that's going to get rid of the dot product between the Gaussian surface and the electric field? A cylinder. Okay, so the best surface is a cylinder. Okay, so let's say this is a cylinder of radius r, and its length is L. Okay, so then we're gonna say that electric field, or Gauss's law, which says E dot dA is equal to the charge enclosed over epsilon naught. Okay, now the charge enclosed is what? So suppose you were given that the total charge on the rod, or we're not given the total charge on the rod, we're just told that it is uniformly distributed. Okay, so I mean, from that information we can define the density of the rod as the total charge on the rod divided by the length of the rod. Okay, so there can be infinite amount of charge on the rod, but the density of the rod, which is the charge divided by length, that does not have to be infinite. Okay, so the charge that is being enclosed by our Gaussian cylinder is the density times the length. Okay, this length, that is the length of the cylinder. Okay, so we can come back here and say that E, and the dot product goes away because E and dA are parallel, and also E comes out of the integral because it's constant along the boundaries of the cylinder, and also there's no electric field to these faces, so they don't matter, this face and this face. Okay, so it becomes E times the surface area of a cylinder, which is 2 pi RL, equals lambda times L divided by E naught. So that implies that E is equal to lambda over 2 pi E naught times 1 over R. Okay, so that is the electric field that is produced by a uniformly charged rod that is infinite in extent. Yeah, I hope Gauss's law was clear. It is not an easy concept. It's something completely new that you haven't seen something like that in Physics 1. So it's a new concept, but I hope this helped. If you have any questions, leave a comment. Next video is going to be about electric potential. See you then.